Now let's discuss about the first law of thermodynamics. It is introduced by Clausius in 1850. The law of conservation of energy is otherwise taken as the first law of thermodynamics. So, the law of conservation of energy in a specific form may be stated as whenever work is converted into heat, a definite amount of heat is produced for every part of the work so converted. It is whenever work is converted into heat, a definite amount of heat is produced for every part of work so converted. That means for every part of work we are doing on the system, then for every part of work we will get a quantity of heat. Similarly, this statement can also be stated like this: when heat is expended to produce work, some amount of heat is used up for every point of or every unit of work so produced. So this is the first law of thermodynamics. It is a particular specific form. It is actually the first law of thermodynamics is nothing but the law of conservation of energy. Energy can neither be created nor be destroyed, but it can be converted from one form to another. But it can be also be stated in this way, that is, whenever work is converted into heat, a definite amount of heat is produced for every part of the work so converted. Similarly, when heat is expended to produce work, some amount of heat is used up for every unit of work so produced. So this can be treated as the statement for the first law of thermodynamics. This thing actually first proposed by Joule as his is known as the principle of heat equivalence. It states that when work is converted into heat, a definite amount of work produces a definite quantity of heat. That is the principle of heat equivalence. It is introduced by Joule. That is, when work is converted into heat, a definite amount of work produces a definite quantity of heat. Mathematically, we can write this statement as W is proportional to Q, where W is the work and Q is the heat. So if W is the work done, then Q is the heat produced. If W is the work done on the system, then Q is the heat produced within the system. If W is work done by the system, then Q is the heat liberated by the system. Then W is equal to J into Q, where J is called mechanical equivalent of heat. So if you consider a thermodynamic process, a part of heat supplied to or work done upon the system goes to increase the internal energy of the system. So in the case, if you consider the case 1 as a adiabatic process, that is work done is adiabatically on the system, the whole of it is used up for increasing the internal energy of the system. Now if work is done adiabatically, the whole of it is used up for increasing the internal energy of the system. Now if the work is done non-adiabatically, then the work done will no longer be equal to the change in internal energy du, but it also used up for doing the external work. That means if work is done on a system adiabatically, it is used up for changing the internal energy. So for an adiabatic process, the W is equal to UF minus UI, which is equal to du, the change in internal energy. But for a case of work done non-adiabatically, the work done W will be equal to, it is used up for doing the external work as well as changing the internal energy. So it will be used up for doing UF minus UI, also doing the external work. Usually it is denoted as PdV. So in order that the result may conform to the law of conservation of energy, it is obligatory to consider that the energy has been transferred in some other form called the heat and is denoted by Q. So when work is done non-adiabatically, then in order to conform to the first law of thermodynamics or law of conservation of energy, we have to assume that the energy has been transformed in other form, transferred into some other form, and that form of energy is the heat. So we can say that the quantity of heat liberated from a system is actually the change in internal energy minus work done on the system. So in differential form, this equation can be written as del Q is equal to du plus del W, or this is equal to du plus del W is the external work done, which is equal to PdV. So this is the mathematical statement of the first law of thermodynamics. The statement for the first law of thermodynamics can be stated in any way. It is same as the law of statement for the law of conservation of energy, or in the context of thermodynamics, by considering heat and work, we can state that when a work is converted into heat, a definite amount of heat is produced for every part of work so converted. Similarly, when heat is expended to produce work, some amount of heat is used up for every unit of work so produced. Mathematically, we can write this as del Q. The change in heat in a process is given by sum of the change in the internal energy and pressure volume work, or the external work, PdV. So this is the mathematical statement of first law of thermodynamics. So which states that heat supplied to a system is equal to the increase in the internal energy of the system plus external work done by the system. So what we have to remember from here is that I told you in the previous lecture that the internal energy has two parts, the internal kinetic energy and internal potential energy. So if you consider an ideal gas, the intermolecular interactions are not there. The internal potential energy is due to the intermolecular interaction or attraction between the individual gas molecules of the system. So the internal energy is fully kinetic or wholly kinetic and for a perfect gas, ideal or perfect gas. Another one is that it is not only the change in internal energy that can be measured in terms of work. That is, we cannot measure internal energy U as such measured, only the change in internal energy, that is du, change in internal energy can be measured. Now for a cyclic process, that is the initial and final stages are the same. Since U internal energy is an state function, then closed integral du will be always 0. Therefore we are having first law, from first law we will have Q is equal to W. The heat applied to the system is used up for doing the work. Hence the system serves as a device for converting quantity of heat Q into an equivalent amount of external work W without itself undergoing any permanent change. In thermodynamics, it is called a heat engine and the system is called a working substance. So this is the principle of a heat engine. So that is all about the first law of thermodynamics. Now we have to discuss about some of the applications and the impact of the first law of thermodynamics. First of all, we will consider how we can derive the equation of state for an adiabatic process. We are familiar with the expression PV raised to gamma, which is is equal to a constant is the equation of state for an for an adiabatic process. To derive this, we can use the first law of thermodynamics. For that, consider a 1 kilogram of a perfect gas. Then from first law of thermodynamics, du is equal to, or we have written in this way, del q is equal to du plus p dv. This is the mathematical statement of the first law of thermodynamics. So now for an adiabatic process, there is no heat liberated from the system or absorbed by the system. There is no exchange of heat between the system and surrounding. So therefore an adiabatic process, del q is equal to 0. Then this equation becomes du plus p dv is equal to 0. Let it be equation number 1. It is actually from del q is equal to du plus del w, where we have taken this del w as p dv. Now let the gas expand, performing an external work p dv at the expense of its own internal energy. So if it uses its internal energy to expand, then its temperature will fall down by, and let dT be the change in the temperature. Then suppose the definition for the specific heat is given by Cv is equal to, the specific heat capacity at constant volume is given by del q by dt or dq by dt at constant volume. The heat exchanged with respect to the temperature at a constant volume. For first law of thermodynamics, we know that del q is equal to du plus p dv at constant volume. Del q at constant volume will be du at constant volume. So Cv can be written as del q by dt at constant volume can be written in this way, du by dt at constant volume. So this can be written as du is equal to Cv into dt. Du is equal, so we can take du is equal to Cv into dt. So this equation number 1 becomes Cv dt plus p dv is equal to 0. That will be equation number 2. Now for an ideal gas, we know that PV is equal to RT, or this can be written as Cp minus Cv into T. We will derive this equation in the next lecture, that is how this R becomes Cp minus Cv, or Cp minus Cv is equal to, for a 1 mole of a gas we are usually using this equation, Cp minus Cv is equal to capital R. For n mole of a gas, Cp minus Cv is equal to small r. So now differentiate this equation, then it will be p dv plus v dp is equal to Cp minus Cv is a constant into dt. So from this equation we are going to write an equation for dt. We need equation number 2. So here dt from this equation is given by p dv plus v dp divided by Cp minus Cv. Let it be equation number 3. Now substitute equation number 3 in equation number 2. That is, for dt in the equation number 2 we are substituting equation number 3. So it will be Cv into P dV plus V dP divided by Cp minus Cv plus P dV is equal to 0. Now we are going to modify this equation by making some rearrangements. Cross multiply this Cp minus Cv to here, then what we will have is Cv into P dV is the first term plus Cv into V dP is the second term. The third term is Cp into P dV and fourth term is minus Cv into P dV all divided by Cp minus Cv is equal to 0. So the numerator alone will be 0 to satisfy that equation. So here we can have Cv into P dV minus Cv into P dV, they will cancel each other. What remains is Cv into V dP plus Cp into P dV is equal to 0. Now divide this equation by 1 by or if it is dividing, it will be Cv divided by P into V. Then if first term is divided by Cv divided by Pv, then Cv into V will cancel. What remains is dP by P plus the second term will be Cp by Cv, P by Pv will be 1 by V dV is equal to 0. Now if you substitute Cp by Cv is equal to gamma, then dP by P plus gamma times 1 by V dV is equal to 0. Now if you consider the differential, that is differential of Pv raised to gamma, it will be, it can be represented as dP into V raised to gamma plus P into differential of V raised to gamma, which will be equal to V raised to gamma into dP plus P into gamma into V raised to gamma minus 1 into dV. If you divide this equation by V raised to gamma or Pv raised to gamma, then first term will be dividing this equation by Pv raised to gamma. This equation will be one by P dP plus gamma times one by V dV. So this term we can write like this: differential of Pv raised to gamma is equal to 0. So differential of Pv raised to gamma is 0, means Pv raised to gamma is a constant. So this is the equation for an adiabatic process. It is the equation of state and adiabatic process. Pv raised to gamma is equal to a constant. It is actually started from the equation del Q is equal to du plus del W, where we have substituted the PdV for del W because we assumed that the gas expands by using its internal energy by doing an external work PdV, and for an adiabatic process del Q is equal to 0. Then for an ideal gas or a perfect gas we use the PV is equal to RT expression for substitution in the change in temperature. Then some modification yields PV raised to gamma is equal to a constant, which is the equational state for an adiabatic process. Now you know that PV is equal to RT for an ideal gas, and for an equation state is PV raised to gamma is a constant. I am representing it as K. Then this equation become P V is RT by P all raised to gamma is equal to constant, then which implies T raised to gamma P raised to gamma 1 minus gamma is equal to K by R raised to gamma. Or T into P raised to 1 minus gamma by gamma is equal to K raised to 1 by gamma divided by R. So this is another constant. So we can write this as T P raised to 1 minus gamma by gamma is equal to some other constant. Let's call it as K1. Now if you consider another substitution, that is for here we have made substitution for V. If you make substitution for P, we can have, instead of P we are having RT by V into V raised to gamma is equal to a constant, which implies RT V raised to gamma minus 1 is a constant, which implies T V raised to gamma minus 1 is equal to K by R, which is another constant K2. So for a adiabatic process, since we can have this equation PV raised to gamma is a constant, or T V raised to gamma minus 1 is a some other constant, not the same constant, and T P raised to 1 minus gamma all divided by gamma is a constant. This is again another constant. Or it can also be written in this way: P1 V1 raised to gamma is equal to P2 V2 raised to gamma, or T1 V1 raised to gamma minus 1 is equal to T2 V2 raised to gamma minus 1, or we can write T1 P1 raised to 1 minus gamma all divided by gamma is equal to T2 P2 raised to 1 minus gamma all divided by gamma. So these are the some of the equations representing the adiabatic process, or equation of state for an adiabatic process, where this gamma for some of the process for a monoatomic gas, it will be useful for doing problems. For monoatomic gas, gamma is equal to 5 by 3, which is equal to 1.6667. Then for a diatomic gas, this is monatomic. For diatomic gas, the value of gamma is 7 by 5, which is equal to 1.4. The example for diatomic gas is air. For air also we are taking gamma is equal to 1.4. Then for polyatomic gas, gamma is equal to 4 by 3, which is equal to 1.3333, and so on. So remember these values for doing the problems. For monatomic gas, gamma is 5 by 3. For diatomic gas and air, it is 7 by 5, and for polyatomic gas it is 4 by 3. So that's all about the first law of thermodynamics and one of the application for the first law of thermodynamics. Thank you.